Hi, are you one of those people who believe that math is not important? Or were you told that math is irrelevant in this world? Well, newsflash, it's either you're wrong or they're wrong. Because math is one of the most significant and essential concepts, especially in the information age where the world is run by technology. From smartphone to computers, it's hard to say that math is irrelevant anymore. You know what? I have an idea. What if I prove it to you? Well, there are a lot of mathematical concepts. It's seen and used everywhere. But let's begin with the machine that you and I are most familiar with. It uses a lot of math and it can be seen in a lot of field. And that is a computer. Well, for one, did you know that your computer generates random numbers? Well, if you knew, did you know why? Computers require and produce random numbers because these numbers serve various purposes. They are used for creating unpredictable results for your computer games, encrypting information, and simulating unknown variables which can be seen in several fields, such as in aviation for airplane scheduling, predicting the weather, and most notably in the medical field. But where do we get these random numbers? If we look closely at our surroundings, we'll undoubtedly find random fluctuations. These fluctuations, also known as noise, can be measured, and with it, we can generate truly random numbers. Let's try and conceptualize a random sequence by closing our eyes and scribbling on a piece of paper. In time, you'll notice a lack of pattern in the scribbles. Therefore, each movement is unpredictable. Hence, random processes are non-deterministic. However, computers are deterministic, meaning each action is predictable and repeatable. So, how can a computer generate random numbers? According to Donald Knuth, in a sense, there's no such thing as a random number. For example, is 2 a random number? Rather, we speak of a sequence of independent random numbers with a specified distribution. Take this for example. To simulate the roll of a die, you'll want to create a sequence of random numbers x0, x1, x2, and so on, each of which has a 1/3 chance of being each number between 1 and 3. So that's the specified distribution. But how can a deterministic computer do that? That is when pseudorandom numbers become handy. These are sequences that look like random numbers but are produced in a deterministic process. There are two types of mathematical concepts for pseudorandom number generation. Those are the middle square algorithm and linear congruential algorithm. So with that, let's begin with the middle square algorithm. In 1946, John von Neumann developed the middle square algorithm. It starts by selecting a genuinely random number called the seed. The algorithm can begin with a 2-digit seed that can generate 100 numbers at most. As you can see here, we have 2-digit seed, and then next we have a 3-digit seed that can generate 1,000 numbers, but it cannot expand past that, as you can see here in our example. However, if the value for the seed is large enough, the sequence can create billions and trillions of numbers before repeating. It occurs when the algorithm reaches the seed it's assigned. This cycle is known as the period. So, how do we solve the middle square algorithm? Let's have an example. Let's say that you assigned a 4-digit number like 5,432 for your seed. You have to square it and get the middle 4 digits. Those digits would be the next term in the sequence and repeat the process. If so it happens that the squared result of the digits is less than 8, fill in leading zeros until it becomes 8 digits long, and repeat the process the same that we did for the first example, which leads us to a formula for all n. Define x sub n plus 1 as the middle 4 digits of x sub n squared. Remember, a 4-digit number cannot expand past 10,000 before reaching its period. With that, let's discuss the second algorithm. The second algorithm is linear congruential algorithm. In 1951, Derek Lemmer developed the concept of the linear congruential algorithm and was later on improved by the Thomson and Rothenberg in 1958. This algorithm requires 4 inputs. The modulus is m, the multipliers is a, the increment is c, and the seed is our starting value. So, how do we solve this? For example, let's assign values 7,829 for m, 378 for a, 2,310 for c, and 4,321 for the seed. First, multiply the seed by a, add c, then take it all to modulus m. Next, you need to look at the remainder when it's divided by m. For example, if we plug in our values to the formula, it gives 7216. Repeat this process to get the rest of the sequence. Then, we get x sub n plus 1 equals a times x sub n plus c modulus m. Therefore, the numbers in the sequence will be between 0 and 7828, which is m minus 1. Now that we know how pseudorandom number algorithms work, let's dig deeper into how they're used in real life. I believe we're all familiar with COVID-19 since it's impacted many families since its emergence. It posed a substantial threat to the economy and the lives of all citizens. So what does the pandemic have to do with PRNGs? PRNGs are utilized in medical simulations, and these simulations use mathematical modeling, one of which is the SIR model. It represents infectious disease and the variables SI and R that stands for susceptibles, infected, and recovered. It is used by PRNGs to generate a sequence for the data collected. Let's imagine we need a series of figures to represent the number of sick people in a specific area of the Philippines. To put it another way, we want to create numbers based on this distribution. Let's try inverse transform sampling, which we can do with our uniform 0-1 sequence. Let's suppose we'll begin with 0.0671 as the first number in the sequence. So we find that the point on the cumulative distribution for the infected with a y value of 0.0671 on the cumulative distribution for the infected. To put it another way, we discover the infected, such as locating the point on the distribution for the infected whose y value is 0.671. In other words, we find that 6.71% of Filipino people are infected. The following number in our sequence is 0.9. As a result, we utilize the cumulative distribution to find the infected, such that 90% of Filipinos are sick, and so on, producing a new sequence. Let's see whether this makes intuitive sense. Well, as you can see, there are a lot of people who have been affected. That explains why the cumulative distribution function there grows so quickly. A steep slope indicates a high probability, while a shallow slope indicates a low probability. We choose a point on the y-axis at random and then find the point on the x-axis that corresponds to the function value. More of those points belong to places with a steep probability slope. Fewer of these correspond to low probability locations with a shallow slope. This quite excellent method allows us to change the distribution of a sequence of uniform 0-1 random, or pseudorandom numbers. Even on a deterministic computer, the genuinely random and pseudorandom procedures we investigated produce numbers with a uniform 0-1 distribution, which in turn produces sequences with different distributions, such as used in dice rolls, game results, weather forecasts, and so on. There you have it. That's the reason why computers generate random numbers, because it's helpful in several fields of work. I hope you learned something today and give more appreciation to these wonderful mathematical notions. As I've shown you, it's already helping us in the form of medical simulation, which is a top priority in this time of pandemic. It also provided us entertainment and comfort in the form of video games. You and I know that math can be pretty intimidating sometimes. Some of you even thought that it's insignificant. But if you try and explore it, you'll love and enjoy how these inventions were created and how they provided convenience in our life. And maybe one day you may invent programs that have a purpose that is very close to your heart. But I guess that should be all for today. Until next time, bye!